Welcome to the deep dive. Today we're going deep, really deep into the heart of matter itself. We're talking about atoms, the tiny building blocks that make up, well, everything.
It's a pretty fascinating journey, actually, from ancient philosophers just thinking about what reality is made of, all the way to modern physics and, well, splitting the atom.
Yeah, and we've got this excerpt from the dawn of the nuclear age to help guide us. I gotta say, some of this stuff is pretty mind-blowing. Like, did you know that even way back in the 8th century BC, ancient philosophers were already thinking about atoms?
Oh, yeah, the ancient Greeks and even Indian philosophers, they had this idea of tiny, indivisible particles.
They called them atomos, which means uncuttable.
It's incredible, right? I mean, no microscopes, no particle accelerators, just pure thought and reasoning. And they were basically on the right track.
It makes you wonder what they'd think of what we know now. All the stuff we've learned about atoms since then.
It'd probably blow their minds. But, it took a long time for those early ideas to become, well, actual science.
Right. It wasn't until the 19th century that a guy named John Dalton really brought those ancient ideas into the realm of science, with his atomic theory.
Dalton's work was huge. He did all these experiments, really carefully measuring how elements combine to form, well, compounds.
And what did he find?
Well, his experiment showed that each element is made up of its own unique type of atom. It was a huge leap forward. I mean, it's basically the foundation of modern chemistry as we know it.
So finally, scientists have proof that atoms exist. But then, well, things get even more interesting. Turns out atoms aren't actually indivisible.
Yeah, that was a big surprise. In the late 1800s, a physicist named J.J. Thomson, well, he discovered the electron
The electron?
and a tiny negatively charged particle. And guess what? It was inside the atom.
Hold on, so atoms weren't just these solid little balls, there was something even smaller inside them.
Exactly. And that raised all sorts of new questions, of course. Like, if atoms weren't solid, how were they structured? Where were these electrons, hanging out inside the atom?
It's like those Russian nesting dolls, You open one and there's another one inside and another and another. The atom was suddenly a lot more complex than anyone had imagined.
That's a perfect analogy. Well, the next layer of that atomic nesting doll was revealed by a physicist named Ernest Rutherford in the early 1900s. He did these really clever experiments where he shot tiny particles at a thin sheet of gold.
So he's basically, what, shooting tiny bullets at a target?
Yeah, something like that. But, you'd think those particles would just pass right through the gold, right? Like, imagine shooting BB pellets at a beach ball.
You'd expect them to go straight through.
Exactly. But that's not what Rutherford found. Some of those particles bounced back, and some of them were deflected at these crazy angles.
So what did that mean?
It meant there was something small and incredibly dense at the center of the atom, something those particles were bumping into. And that's how he discovered the nucleus.
The nucleus.
Yeah, the tiny, dense, positively charged center of the atom. It was a huge discovery, totally revolutionized our understanding of the atom.
So we go from thinking of atoms as these solid spheres to realizing they have this tiny nucleus in the middle. It's like finding a tiny marble inside that beach ball.
Exactly. And that's where we'll pick up next time. We'll delve into the discovery of the neutron and all those forces that hold the atom together.
Sounds good. It's already getting pretty complex, and we haven't even talked about splitting the atom yet.
Oh, yeah, that's coming up. And, splitting the atom, that's a whole other level of mind-blowing.
Well, you've definitely got my attention. See you next time for part 2 of our atomic deep dive.
See you then. Welcome back. Last time we left off with this whole new picture of the atom with its tiny, dense nucleus.
Right, the nucleus. But you sort of hinted that there's more to the story.
Oh, yeah, the atom had a few more secrets to reveal.
Yeah.
And, they turned out to be some pretty world-changing secrets.
Okay, so spill it. What else is going on inside the atom?
Well, in the 1930s, a physicist named James Chadwick, who was, working with Rutherford, he discovered another particle hiding out in the nucleus.
Another particle? Okay, what is it this time?
The neutron.
The neutron. Okay. But wait, I thought we already had the protons and electrons, so what's so special about this neutron thing?
Well, the neutron, see, it has no electric charge.
No charge. So how did they even find it if it's, like, electrically neutral?
It was tricky. It was like trying to, I don't know, spot a chameleon that's perfectly blended in. It took some really clever experiments to finally pin it down.
So why was it so important to find this neutron?
Well, the neutron was the missing piece that really allowed scientists to understand, nuclear reactions.
Nuclear reactions. Okay, and I'm guessing this is where things start to get really interesting, maybe even a little bit scary.
You could say that. One of these reactions, nuclear fission, well, it turned out to be incredibly powerful.
Fission, so we're talking about like splitting the atom.
Exactly. Splitting the atom, or more specifically, splitting the atom's nucleus. And when that happens, a tremendous amount of energy gets released.
Wow, okay, that's huge. So who figured out how to do that? Split the atom?
It was actually a bit of a team effort. There was this Austrian physicist, Lise Meitner. She played a key role. She was working with a team in Germany, and they were bombarding uranium atoms with
With
neutrons.
neutrons, okay.
And
Well, they observed something amazing. The uranium nucleus, it was splitting. It was like, imagine they're doing these experiments and suddenly they realize, whoa, we just split the atom.
yeah, I bet that was a pretty mind-blowing moment.
Yeah.
Certainly, they have access to this incredible source of power, unlike anything anyone had ever seen before.
Right. And the thing is, this discovery came at a really, well, sensitive time. World War II was already raging.
Uh-oh. So I'm guessing people quickly realized that this new power, this splitting the atom thing, it could be used for, more than just generating electricity.
Exactly. The potential for destruction was, well, was pretty obvious.
Yeah, I mean, we're talking about the atomic bomb here, right?
Yeah.
It's kind of a dark side to this whole atomic story. Definitely. And that's how the Manhattan Project got started, the top secret effort in the U.S. to develop the atomic bomb.
It's pretty wild to think about all those scientists working feverishly to build this weapon of unimaginable power. I mean, it really shows how scientific discovery, it can be a double-edged sword.
Yeah, for sure. On one hand, you have this incredible potential, but on the other, there's this responsibility that comes with it.
Right. I mean, the Trinity Test, the first atomic bomb detonation, it was more than just an explosion, wasn't it?
It was a culmination of, centuries of human curiosity and inquiry. I mean, from the ancient Greeks who first imagined atoms to the modern physicists who finally figured out how to, unlock their secrets.
So it's like we finally reached this point where we understand the atom, we can manipulate it, but then we unleash this incredible power, this force that could, well, literally change the course of history.
And it did. The nuclear age had begun. But, the quest to understand matter, it didn't stop there.
Wait, there's more? I mean, we've gone from these solid, indivisible atoms to realizing they have this tiny nucleus. Then we figure out how to split the atom, unleash all this energy. What else could there possibly be?
Well, it turns out protons, neutrons, and electrons, those weren't the end of the story. Physicists started to discover even smaller particles.
Even smaller. So it's like we're going deeper down the rabbit hole into a world that's, well, even stranger than we thought.
Exactly. And as they delved deeper into this subatomic world, physicists uncovered a whole zoo of particles, all these weird and wonderful particles. It was almost like, too much information.
I can imagine it's like you think you've got it figured out, and then bam, a whole new set of questions pops up.
That's science for you. Always pushing the boundaries. But, even in all that chaos, patterns started to emerge. And one of the key figures in making sense of it all was a physicist named Murray Gell-Mann.
Okay, so what did Gell-Mann do?
Well, he proposed the existence of something called quarks.
Quarks. Okay, that sounds kind of quirky. What are quarks?
They're even tinier particles, the things that make up protons and neutrons. Like, think of them as the building blocks of the building blocks.
So we're talking about like the sub-basement of the atom here.
Pretty much. And, the name quark, it actually comes from a line in James Joyce's Finnegan's Wake.
Finnegan's Wake. That's pretty random. What, were physicists just hanging out reading James Joyce in their spare time?
Apparently. But hey, it's a catchy name, right? And it's stuck. So yeah, we have quarks, these tiny particles that make up the protons and neutrons inside the nucleus.
Okay, so quarks, got it. But where does that leave us? I mean, we've got all these particles now, these quarks and electrons and neutrons, and how does it all fit together?
Well, that's where the standard model of particle physics comes in.
Yeah.
It's our best attempt so far to explain all these fundamental particles and the forces that, govern them.
The standard model, okay, but is that the end of the story?
Not quite. As with all good scientific theories, there are still some mysteries that the standard model can't explain. And that's what we'll explore in the next part.
Sounds intriguing. I'm ready for more.
It's kind of amazing when you think about it, right? Like, everything we see, everything we touch, it's all made up of these tiny particles we've been talking about. It's kind of mind-boggling.
It really is. I mean, we just assume the world is, well, solid. But when you get down to the level of, atoms and quarks and all that, it's mostly empty space.
And it's all governed by these forces we can't even see. It's like,
Yeah.
what is reality even?
Right. It gets pretty weird down there. And, last time we were talking about the standard model of particle physics, and you mentioned that it has some gaps, things it can't explain.
Yeah, the standard model. It's like our best theory so far, but you said it's not the whole story, right?
Yeah, it's a good theory, don't get me wrong. It explains a lot. But it's like, a map with some blank spots. There are things out there in the universe that we observe, but the standard model just doesn't have an explanation for them.
Okay, so what are these mysteries? What are we missing?
Well, one of the biggest mysteries is something called dark matter. Dark matter. Okay. I've heard of that. But remind me, what is it exactly?
Well, we know it exists. We can see its effects. Like, we observe galaxies and clusters of galaxies, and the way they move, it just doesn't make sense based on the amount of matter we can actually see.
So it's like there's this extra gravity out there coming from something invisible.
Exactly. There's all this mass out there that we can't see, but we know it's there because of its gravitational pull.
So what is it? What's this dark matter made of?
That's the big question. And, the standard model, it doesn't really have any good candidates. So physicists are coming up with all these new theories, all these new particles that could be out there.
New particles. So we're going even deeper now, beyond the standard model.
Yep. One idea is that dark matter is made of something called WIMPs.
WIMPs.
Yeah, it stands for weakly interacting massive particles.
Okay, so they're massive, but they don't interact much with, well, regular matter.
Right. They're all around us, passing right through us, like ghosts.
Spooky. So how do we find these WIMPs if they're so hard to detect?
Well, scientists are building these incredibly sensitive detectors deep underground, shielded from all the noise and radiation. It's like trying to, hear a whisper in a hurricane. But if we can find them, it would be a huge discovery.
So dark matter, that's one mystery. But I think you mentioned there's another one, right? Something about dark energy.
Oh, yeah, dark energy. That's a whole other can of worms.
So what's dark energy?
Well, basically, it's the name we give to whatever is causing the expansion of the universe to accelerate.
Wait, so the universe is expanding?
It is, yeah. And it's not just expanding. It's expanding faster and faster all the time.
Faster and faster. But I thought gravity would, slow things down.
You'd think so, right?
Yeah.
But there's this mysterious force that's actually pushing things apart, overwhelming gravity on these cosmic scales. And that's what we call dark energy.
Okay, so we've got dark matter, we've got dark energy. It's like the universe is mostly made of stuff we don't even understand.
Pretty much. And here's the crazy part. Dark energy, it makes up about 70% of the total energy of the universe. And dark matter, that's another 25%.
So everything we can see, the stars, planets, everything, that's just 5% of the universe.
That's what it looks like.
Wow. That's just, I don't even know what to say. It's mind-blowing and kind of humbling,
Yeah, it really puts things into perspective. It shows how much we still have to learn.
So, okay, let's go back to those quantum fields you mentioned earlier. You said that particles might not be solid objects, but more like fluctuations in these fields. What does that even mean?
Right. Quantum fields, it's a bit of a tricky concept. Imagine, a vast ocean, and particles, they're like waves on the surface of that ocean.
So the waves, they come and go, but the ocean is always there.
Exactly. And that ocean, that's the quantum field. It's this fundamental fabric of reality. And particles, they're just like little disturbances in that fabric.
So basically reality is way more, I don't know, fluid and dynamic than we think it is.
I think that's a pretty good way to put it. It's not all neat and tidy like we thought.
So, I mean, after all this, where do we even stand? We've gone from thinking atoms are these solid, indivisible things to this whole quantum world of fields and dark matter and dark energy. It's like, I thought we were trying to figure out what matter is, but now I'm not even sure what reality is anymore.
Well, that's the fun part. It just shows that, we're constantly learning, pushing the boundaries of what we know.
Well, I've got to say, this deep dive into the heart of matter, it's been a wild ride. We've gone from ancient Greek philosophers to the mysteries of dark matter and quantum fields. I'm definitely leaving with more questions than answers, but that's okay, right? That's how we learn and grow.
Absolutely. It's all about asking questions, exploring the unknown, and who knows what incredible discoveries lie ahead.
So to all our listeners out there, thanks for joining us on this incredible journey into the heart of matter. It's been fun, it's been fascinating, and it's definitely given us all a lot to think about.
Yeah, and keep those brains buzzing. The universe is full of mysteries, and we're just getting started.